So today we'll be talking about algebraic manipulation. So we'll be continuing with this topic. I strongly recommend you, recommend you to watch the previous videos on this before watching this video because it'll be good kind of taking small steps towards mastering this technique. And also I might be referring to that video. So if you don't want to be confused, then watch the first and second video. So today we're going to be looking at some more complex identities that some people starting competition math may likely not know. So for example, I'll just write them down. So first is the cubic ones, which is the sum of the cubes. This is just this. So I'll just write the identities down because there's no way to really prove them because you can just expand it yourself and see what happens. So starting off with the cubic ones. We have these. Actually, these two are pretty obvious. It's just binary expansion, and also, but these are a bit less seen in junior competition math. But you should be really familiar with these because it's very important. So the main important thing about this is that before we looked at how these expressions are not about relating x and y, but it's more about relating expressions to each other. So this equation, so the first equation, for instance, if we know the sum of two cubes, if we know the sum of the cubes of two numbers, and the sum of those two numbers, and we also know the product of those two numbers, then we can plug those values in, and then we can find the sum. So x squared plus y squared. We can find the sum of their squares. So if we know the sum of their cubes, we know the sum of them, we know the product of them, then we can find the sum of the squares, sum of their squares, which is very neat and very symmetrical as well. So we can see that before we had this. If we have the sum, if we have the difference, then we can find the difference of the two squares. So it's another way, but higher degree, to find the value of expressions based on other expressions. And similarly with these. And this is similar as well. And for this one, for the last two, so it's kind of difficult to see this kind of expression like x squared y plus xy squared. So you can rewrite this as this. Then this identity becomes essentially the same as this one, because you can see that just like this one, if we know the sum of the two numbers, if we know the sum of their cubes, and then we know this, and we know their product. Oh wait. Oh no, this one's different. So this one and this one. So in this one, we see that we can find, if we know sum of the cubes of the numbers, and we know the sum of their product and their sum, then we can find the sum of their squares. But this one is it has less variety of expressions. So here, this time, if we know the sum of the two numbers and we have the sum of their cubes, we can straight away find the product of those two numbers from this. So we can neatly similar to this one, but it relates less expressions together. But this means that if we want to find the sum of the squares from like these three values, then it's more appropriate to use this. Or if we just have x plus y and x cubed plus y cubed, and we want to find xy, then we don't have to use this. We can just straight away use this. So actually, the way I'm explaining this technique is kind of AMC style, because the reason I call it AMC style is because AMC is a really fast-paced test, which means that you need to know the really, really fast techniques without needing to derive them on the spot. So one of the reasons I don't like AMC, but also the fast pace kind of gives you a sense, kind of forces you to think creatively. So I guess it is a very good contest, but I think the lack of time can sometimes be not that good as well as sometimes. So basically the main message is that yes, you can derive them on the spot. Like actually, if you know x cubed plus y cubed and you know x plus y, then you can put x squared plus y squared in terms. You can put x squared plus y squared in terms of x plus y and x times y, and then do something to find x times y from this. Like you can easily derive these. So it's kind of so some good mathematicians will think, oh, what, like these two can be derived from each other very easily. So why would I need to remember that these relate different expressions somewhat? Well, because it's nice to just think of these quickly and just remember by heart from doing many problems on memorizing that these few expressions are related and these few expressions are related. Yeah. So those are the cubic expressions, and then we're going to look at the higher degree ones. So we're going to generalize it. We're going to say x to the n minus y to the n, two different ones, and then x to the n plus y to the n. So for this one, for the first one, it's any n. Well, I guess any n. And then for the second one, it's for even n. And with the third one, it's odd n. So we're going to see what they are. So you can actually, for all of these as well, like if you want to confirm or just check if I'm wrong, then you can just expand on your own to see if they do become this expression. So x to the n minus y to the n is actually equal to x minus y times it's equal to this. Oh my god, I don't think I have space, but so basically it's just x minus y times the power of x decreasing by 1 every time, and then the power of y increasing by 1. And the degree of this polynomial here is n minus 1, but it's basically kind of like the binary expansion thing, except that the coefficients are all 1, and then the degree is n minus 1 instead of n. So you might be seeing these kinds of formulas, some expressions sometimes. So yeah, it'll be good to remember those so that you can relate x to the n minus n, y to the n to x minus y. And then for even n, this becomes, again, I'm gonna write less of the terms. So it's the same as this. It's the same as the first one, except that it's x plus y. And then here, the minuses and pluses are alternating with the plus at the beginning for x to the n minus 1. And the reason, so x to the n minus y to the n is always equal to this, but then if n is even, then we can also write it like this. So it depends on our choice. Like if n is even, then we have to look at, oh, are we looking for x plus y or this expression? Like always think about which expression will be better to use. And then for x to the n plus y to the n for odd n, it is x plus y times x to the n minus 1 minus x. So it's exactly the same as this, except that exactly the same as this, but oh, that's a plus. Yeah, so since n is even, then at this point, this should be a minus after all the alternations. And then here, since n is odd, after all the alternations, this should be a plus. So those are all the identities. And so actually, you can use these. You can use these to confirm, just verify these two. And you can verify these two equations by using n equals 3 by knowing that these two equations are true. And then, yeah, so I think in the next video, we're going to actually look at interesting problems to do. But this video was just an introduction to more of these identities. So actually, these are not just needed in algebraic manipulations. I think I'll just talk briefly about these last few equations, the significance of them. So most of the time, I really wanted to just introduce this in number theory, but there's an interesting fact. Most of the time, we don't really look at this expression. No one really cares about this expression, but if x and y are integers, then we always know that x minus y will always divide x to the n minus y to the n. And this is a very important fact in number theory. But yeah, because I think this is one of the first videos where I introduced these identities. So I'm just saying it as a fact. Normally, it's good to use these expressions in algebraic manipulation, but most of the time, I think these are more applied in number theory, but here they're just here for reference because it's similar. It's a part of all the techniques that we'll use in algebraic manipulation. So yeah, that is the end of this video. I hope you enjoyed this video, and I hope to see you in the next video where we'll be actually solving problems using some of these identities.